Hello, today's topic is the Graham-Schmidt algorithm, material from 6.4. So this is an important algorithm in linear algebra attributed to, I think these are two mathematicians. Not sure if they invented this, but they get their name on it. The idea here is that suppose we're given a basis B for some subspace H, maybe, and let's say living in Rn. We often want to convert B into a orthogonal, or even better, an orthonormal basis B prime. And why would we want to do this? Well, we saw last time, our main application will be that if we have an orthogonal basis for a subspace, we know how to project vectors onto H. So there's other reasons to do this, but that's going to be our main application. And we saw last time that if you have a orthogonal basis for a subspace, then there's a nice formula that tells you how to project a vector onto that subspace. So let me do this with an example. So if H is the span of, let's say, x1 and x2, where x1 is 3, 6, 0, x2 is 1, 2, 2, then let me try to draw kind of a cartoon picture here. So, I've got these two vectors. I don't want to try to draw the three-dimensional coordinates. It'll just get too busy. But, I've got these two vectors in 3 dimensions. They span a plane, right? So the span of those two things is a plane. Call that H. And, the idea now is that this is a basis because it's a linearly independent set that spans H. But notice that x1 dot x2 is what? It's 3 plus 12. It's 15, which is not 0. This is not an orthogonal set. But notice that, think back to last chapter, notice that x1, right, determines this line. So if we have a collection of vectors, it determines a subspace. And if I project x2 down onto this line, so let me indicate that vector there with red, notice that the projection, this will be the projection here, this is what we called x2 hat, I think, right? Well, that projection gives you this other vector that we often called z. I'll call it z for now. We're going to call it something else in a second. But notice that this vector z is orthogonal to the vector x2, and it lies in the plane, right, determined by x1 and x2, because z is a linear combination of the two vectors, right? In fact, we know that x2 hat plus z equals x2. Okay, so the idea is that we're going to now let's create an orthogonal basis. And let me call it v1, v2 as follows. So here's kind of the step-by-step procedure. Step 1 is, well, it's easy. I'm going to just take v1. I have to tell you what these vectors v1 and v2 are. I'm just going to take v1 to be x1. So whatever your first vector is, I'm just going to take that vector, throw it into my collection. Step 2 will actually be the last step here. Will be I need to tell you what v2 is. But notice that, right, what we're going to want is, of course, this z is the one I'm going for. This is going to be my v2. And we know that v2 plus the projection is x2. So what I'll do is I'll take v2 to be x2 minus the projection. So let me call that projection of x2 onto that space determined by v1. Now what is that? Well, that's x2 minus, x2 dot v1 divided by v1 dot v1. That's the number that I scale v1 by, right? So that's just my formula for projecting a vector onto in this case, one-dimensional subspace. Let me actually work that out. So this is 360 minus x2 dot v1, which is 3 plus 12, I think it's 15, divided by v1 dot v1, which is 9 plus 36, 45, times the vector v1, which is 360. And this will be sorry, my x2 should be 1, 2, 2, right? Sorry, 1, 2, 2. Something looked funny there, right? x2 is, of course, 1, 2, 2. Okay, so let's see if I did this right. This should now come out to 0, 0, 2, right? Okay. Yeah, so that should be x2, which is the vector 1, 2, 2. Okay, so what is it telling me? That B prime is the collection of V1 and V2, so it's 3, 6, 0, and 0, 0, 2. And you can see that indeed that's an orthogonal basis. The dot product of those two is 0. And the span of those two vectors is still the plane H because, well, I got this vector as a linear combination of the two basis vectors that I was given. So that's the general idea. Let me give you the sort of general setup. So in general, if we have given B is x1, x2, let's say there's R vectors. If this is a basis for a subspace, say H, then we create an orthogonal basis V1 through VR. And if you think back to that example we started with, what's actually happening here is that every time I throw in a new vector, I create a subspace that was the span of the vectors I've so far seen. So what I mean by that is if I look at the span of V1 through, say, Vj, so if I just take the first j of those new vectors, that's actually the span of the first j vectors you gave me. So notice here that order matters, that I have an ordered list of vectors that are given to me, and I create an ordered list of vectors that forms an orthogonal basis with this property that the first j vectors span the same thing as the first j vectors of what you gave me. And I'll just say, loosely speaking, so what we do is we took v1 to be x1, v2 was, let me write this down, so what is v2? So v2 we saw was x2 minus this projection, right, x2 dot v1 divided by v1 dot v1, and that's what I scale v1 by. That's the projection of x2 onto that subspace determined by v1. And then v3 would be, well, it's going to be x3 minus the projection of x3 on what I have so far. So if you think about that, that's going to be, the same sort of thing with my v1s and v2s now. So this would be x3 dot v1 divided by v1 dot v1. This is x3 dot v2 divided by v2 dot v2. So this, again, is the projection. See if I can circle this. This is the projection of x3 onto, I won't write it here, but this is the subspace determined by, subspace, said I wouldn't write it, but now I am, subspace determined by v1 and v2. Okay, and dot, dot, dot. So now if you had, 100 vectors, you'd keep doing this, it would get a little bit nasty, but in the end, you get your orthogonal basis. Now, to make this thing, to make the basis orthonormal, once you have it orthogonal, you just scale. So just going back to that example from last time, we had B prime was 3, 6, 0, 0, 0, 2. This is an orthogonal basis. How do you make this orthonormal? Well, you just scale each vector by its length. So the length of this vector is, so this is what I call V1, V2. The length of V1 is, of course, the square root of 9 plus 36 is the square root of 45. V2 had length 2, right, square root of 2. So I would just scale this guy by 1 over root 45, 3, 6, 0, comma, 1 over 2, 0, 0, 2, which of course is an easy one to do. But, again, I can just scale things to now get an orthonormal basis. Okay, so that's the idea here. Well, of course, I can simplify this. So 1, this is the same as 1 over 3 root 5, 3, 6, 0, 0, 0, 1. Okay, so that's how you get an orthonormal basis. Again, you can always do that at the end by just scaling everything. Let me just show you kind of one more example, just some numbers to show you how this works for a bigger example. So given, let's say I was given 1, 1, 1, 0, 1, 1, 1, just to have a concrete, some numbers to see. If this was a basis for a three-dimensional subspace of R4 now, so what I'm trying to do now is bring back my general recipe. So remember, my recipe said that to get my new basis, I would take, if this was x1, x2, x3, v1 would be just the same as x1, so that would be 1, 1, 1, 1. And then, I'm not going to go through the calculations now, but what would happen now is that v2, if you apply this calculation, v2 would be minus 3, 1, 1, 1. And then v3 would be, again, the projection of this guy onto the subspace that's determined by x1 and x2. It turns out what you get here is 0, minus 2, 1, 1. Okay, and so this gives you the basis 1, 1, 1, minus 3, 1, 1, 1, and 0, minus 2, 1, 1. And you can check that that's now an orthogonal basis. Every dot product is 0. Okay, so that's the idea behind Gram-Schmidt. Take a basis, produce a orthogonal basis, and that's useful for us, especially in the context of projections. We'll see you next time.